I have absolutely no idea why that last video cut off early. We're going to continue on though. So, moving a force along its line of action has no effect. However, if we move a force to a point not on its line of action, we must include an appropriate couple moments. What do I mean by that? If I have some object, and I've got some force F applied to it, and if the length of this object has a height d, distance, if I were to move this force, if we move a force to a point not on its line of action, so its line of action is down here. So if I move this force to, say, the other end of this object, so I move this force up here, force F. Now it was, move this distance d. So it was down here. Now it's up here. And keep in mind that this force was trying to cause a counterclockwise rotation of this thing. Well, now that I've moved this force up here, it's not necessarily causing the same type of rotation. So to preserve that rotation, I need to include a couple moments in the amount force times the distance that it's moved, FD, which I should have drawn. I guess I should have drawn it over here. I don't know why I drew it right on top of the shape. You've got some couple moment FD. If I have, for example, and we've just mentioned this concept of the couple moment itself, for example, if we look at couple moments, right, that's a good kind of demonstration as to something we just talked about. If I've got some object like this, I've got force F here and I've got force F there, and they are separated by some perpendicular distance d. They're equal and opposite. They're equal amounts pointed in opposite direction. So if I were to move one of those forces off of its line of action, so this guy, let's say we move this guy. So we move him over here. So now I've got force F here. I now have force F there. It's been moved now a distance d. Now over here, note that these guys were trying to cause a clockwise rotation as they're drawn. As they're drawn here, they're no longer trying to cause a clockwise rotation. They're canceling each other out. So to have the same thing that I have here, to try to generate what we call an equivalent force system, if I move a force to be the equivalent of this, I need to include the couple moments. And again, these guys are trying to cause a clockwise rotation. So I need to apply a clockwise moment in the amount of the moment that I've now canceled out. That is this force times distance d, because I've moved this force now over here at distance d. So I need to replace that, or at least I need to preserve the moment that this force was causing. This force was causing moment FD. It's no longer causing that moment FD when I move it here. So I need to add, for this to be an equivalent force system, I need to add that there. And again, we talked about when we introduced the concept of a couple, notice that these two forces now are equal and opposite. They're pushing right against each other. They're no longer doing anything, essentially. And I've preserved the rotation that we were trying to impart by adding this couple moment FD. And notice these forces now, they're canceling out. There's no need to include them here. These are the same things. These are all what we call equivalent force systems. So if again, two main rules here. If you move a force along its line of action, no further action needed. You can move at no cost to you and no consequence. You can move a force along its line of action. But if you move that force off of its line of action, you've got to replace it with an appropriate moment that force was imparting in its original location. Okay. So that's the basic idea. That's the kind of the whole idea, and kind of the remainder of chapter 4 at this point. Now, if we start putting some numbers to these, let's work some problems here. So a lot of these problems might take this form, where you'll see a bunch of these in the textbook, where they'll give you some structure. So we've got what we call a fixed support. It's basically a pole coming out of a wall. Somehow it's really attached to a wall structure. We'll call this point A over here on the left. And let's say we apply some force kind of right in the middle of this. We'll say 100 pounds. And we apply some force over here at the far end of this, 200 pounds. And this is a 10-foot long pole. So 5 foot out here, 5 more foot out to the end. So 10-foot long pole. And the problem might say something like this. Replace the system of forces with a single force located at A and a couple moment. Okay. So what does that mean? Well, that means what I'm trying to do is, again, we mentioned earlier, if you move a force off its line of action, you need to include an appropriate couple moment. So I've got two forces that I'm going to move back here to A. Now you can do this just about any way you like. Just to kind of overkill this a bit, I'm going to move this 200 pounds to the middle and say, well, I could just call it 300 pounds right in the middle, a distance of 5 feet. That's the same as this, so long as I preserve the fact that I've moved 200 pounds a distance of 5 feet. So it was trying to cause a clockwise rotation, so I need to preserve a clockwise moment of 200 pounds times 5 feet. That is 1,000 pound-feet, or a kip foot if you like. Yeah, see, I'm in here. You can come in here. Now, again, you can go. If we go step by step, you can skip all the way to the end on this if you like. But if we go step by step, now let's take this 300-pound force and let's move it the final 5 feet to get back here at point A. So if I take this 300 pounds, move all 300 pounds another 5 feet now, well, I've got to preserve this 1,000 pound-feet out here at the end. But now I've taken 300 pounds and I've moved that 300 pounds another 5 feet. And again, that 300 pounds, because I've moved it from here to here. So at point A, so from point A, A being here. So at point A, this thing is trying to cause a clockwise rotation. So now that it's at A, it's no longer trying to cause that clockwise rotation. So that means I need to keep this equivalent. I need to include the clockwise rotation this was trying to impart in the amount of 300 times 5, that is 1,500 pound-feet. Right? What they really want is they want a single force and a single couple moment. Here I've got one force located at A, but I've got two couple moments. Again, this is a bit overkill. If you're comfortable just skipping to this final step where you say, well, you know what, it's a total of 300 pounds at point A, and it is a total of 1,500 plus 1,000, 2,500 pound-feet, or 2.5 kip-feet. And this would be kind of your final answer. You can also do it this way. You can say, you know what, let's take this thing and let's do sum of forces in the y direction. That is minus 100 pounds, minus 200 pounds, for a net result of minus 300 pounds. And because I'm going to move those forces now to point A, I need to figure out what is the net or resultant moment about point A. So if I look here, if I look at what's the resultant moment about point A, well, I've got 200 pounds out here at a distance of 10 feet. 200 pounds at 10 feet, and that's causing a clockwise rotation. So that is minus 200 pounds at a distance of 10 feet. And then I've also got this one trying to cause a moment about point A, that is 100 pounds, trying to cause a clockwise or a negative rotation. So a negative rotation of 100 pounds at another 5 feet. If you add this up, your net moment about point A is going to be minus 2,500 pound-feet, which is what we found here. So I've just done this graphically. But this is how you do it mathematically. You say, well, they want an equivalent force at point A, so I just need to add up all my forces, and I need to sum my moments about point A. Add them all up. The sign tells you it should be a clockwise rotation. And there we go. That's not a bad place to stop. And I'm going to see if I can see what Izzy's doing back here. Come here. Say hi to everybody. Izzy says hi. All right, guys. We'll be back in the next video.